Okay, so I wanted to take a little bit of time to talk about these sequences and series and divergence and convergence. I haven't had a chance to really kind of give you the whole overview. This stuff is important, and we're building a foundation, and it may not be confusing yet, but it is important to have all those pieces into place because when we get to the tests that come up this week and next week, it could get confusing. Okay, so hopefully this is a helpful video. I found my notes from last year, and I thought that could be kind of a nice way to think about it. What were, and this is the moment in the classroom in the past that I've said, this becomes a trust exercise. You just have to kind of trust that we're going somewhere, that this stuff does matter, but for a little bit of time, it's going to be confusing as to why it matters or what we're actually doing. A lot of the questions we're asking is a binary question. Does this series converge or does it diverge? Okay, and so if it converges, that means that it adds up to a finite amount. If it diverges, it means that it does not. Okay, so what I said, I used these symbols last year. This anytime something converged, I gave it this symbol, although that one isn't as much fun. When something diverges, then we yelled boom because it blows up in your face and you can't add it up to a finite amount. The easiest, the most common series that you all know about is the geometric series. A geometric series is one that has a common ratio from one term to the next. It's multiplicative. And what happens with the geometric series is that if it has a common ratio less than 1 in absolute value, then it's going to converge. And if not, it's going to diverge. That is not too bad. Then we have the divergence test, okay? The divergence test, I call it the duh or the no-dir test. The divergence test is really just stating the obvious, okay? If it says if a sequence converges to anything other than 0, then the series must blow up or diverge. And if you think of the sequence of, let's say, point 1, let's say I have the sum, if I'm, let's say just the sum of point 1 over and over again. Actually, I'm confused as to how I would write that, but a sequence that goes point 1, point 1, point 1. What you should be able to know, and it goes on and on like that forever, is that if you add all these things up, plus point 0.1 plus point 0.1 plus point 0.1, even if it's a very, 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 very small amount, that series is going to diverge. Now, the divergence test is fairly obvious. It also is fairly powerless. There aren't many situations where you're going to be like, the divergence test is my friend because it helps me. Well, I should restate that. The divergence test is always the first one that gets you out of doing a lot of work. Like if you have a sequence that doesn't go to 0, you can say, but every fool knows that it diverges, and you have to state that it's because of the divergence test. A lot of the AP questions that you have to state it. Okay, so what it doesn't show, what a lot of people sometimes think, is that if I have what it can't prove is if something converges. And so the example I used before was 1 over the natural log of n, right? So sum as n goes from, I think this one has to go from 2 because the natural log of 1 is 0. But what you might think is that, I think it's the converse of the divergence test is true, but it's not. So if I have the converse of the divergence test would say if I have a series if I have a sequence that the terms go to 0, then the series converges. However, this is the most common one that I can think of. This, if you look at it, it diverges. It just keeps getting bigger and bigger. And while it does get bigger and bigger by a smaller and smaller amount, there's never a threshold value that it doesn't pass through. No matter what, you could say the series is never going to get over 1 million. And if I wanted to spend all day sliding a slider across a Desmos screen, I could get past 1 million. And then you could say, oh, okay, but it's not going to get past 1 billion. I would not take the bait, but if I were a fool and I took your bait, I could spend all day on Desmos and I could show you that series gets over 1 billion. Okay, so the divergence test does not show convergence. By the way, one other series that we talk about a lot is this one. This is the harmonic series. Okay, and this is 1 over 1 plus 1 over 2 plus 1 over 3 plus ... And you should just kind of commit to memory that that's called the harmonic series. And this diverges also. And if you kind of think of this series is sort of like the cutting off point. I'll tell you this more about the P series, but if you think of 1 over n squared, well, that's going to get small much faster. That's going to be 1 plus 1 fourth plus 1 ninth. Plus, and you can see the terms are getting much smaller, much faster. This one converges. If I think of something else like 1 over square root of n, this is going to be 1 plus 1 over root 2 plus 1 over root 3 plus ... And you can tell that this at every step of the way is bigger than the harmonic series. So if it's bigger than a series that diverges, this one is also going to diverge. And you could rewind and listen to that again and think, if a series is smaller than one that converges, it also converges. If a series is bigger than one that diverges, at every step of the way, it also diverges. That takes your brain a little bit of time to grapple with, but that also lays the foundation for another test that we're going to come back to in the future. However, we've done with the divergence test. Divergence test makes things go boom. It doesn't test that it converges. However, there is this thing called the alternating series test. And so we're going to define an alternating series if it has a -1 to the n. Or there's other ways to make it to encode in your series that it alternates. We'll talk about what all those are. But if I think of what's happening with an alternating series, it's jumping back and forth over some kind of line. And so if it's going to go from positive, let's say if it's an alternating series and the non-alternating part, just this part, that's the non-alternating part. If that part goes to 0, then you could think of, if it wasn't alternating, that could just keep getting bigger and bigger. But if it's alternating, let's say my first estimate is positive, right? If the non-alternating part is decreasing and going to 0, my next estimate is going to be a little bit below that line, okay? And then my next estimate is going to be above that line, but a little bit less. And then my next estimate is going to be below that line, but a little bit closer. And you can see that this is converging because it's bouncing over back and forth from positive to negative. In an alternating series test, it is enough to say that if the non-alternating part goes to 0, then your series converges. And I think I can probably do something on Desmos that speaks to that. I wish I had a poem to write or recite or something while I'm trying to navigate these murky waters in front of your faces. Let's see. All right, so I'm going to go sum from n is equal to 1 to 100 of 1 divided by natural log of n. And immediately doesn't like that, so I'm going to say that. Let's say I'm going to change this to A. I'm going to add a slider for A, and I'm going to change this slider up around. And let's see what's happening is this, it keeps getting bigger. And I'm not going to spend all day doing this, but I'm just going to promise you that there's no number that I can't get over if I did that. Now, if I put in, and let's go back, let's make this more like, let's go from 1 to 10. And if I put in an alternator, is also a part in a car that I believe regulates the electrical flow. If I put in -1 to the n, then that's going to jump back and forth between positive and negative. Let's see, I need this to go by steps of 1. And let's say as what happens as I go up, it's 1.44, then it's 0.53, then it's 1.25. So there's a line that it's approaching, and it's getting closer and closer to that at each step of the way. So I think a lot of times what's confusing about this section is you're like, well, what is that value? And that's part of the trust exercise, is that you just don't need to know what that thing converges to a lot of times. You just need to know that it does converge. Okay, so that's the alternating series test. So far we've had the divergence, we have the alternating series test. You could look at this and you can kind of quickly say, is this an alternating series? Yes. Does this part go to 0? Yes. So I'm going to say converges. Is this an alternating series? Yes. Does this part go to 0? Bigger powers on the bottom. So I'm going to say yes. That's a convergent series. You could look at this and say, is it an alternating series? Yes. Does this part go to 0? No. So that's diverging. Does this part go to 0? Yes. So that's converging. Does this part go to 0? Well, in this case, you have to know what dominates between an exponential and a factorial. And if you can think of what is 2 to the n, it's going to be 2 times 2 times 2 times 2 n times. And n factorial is going to be n times n minus 1 dot dot dot. You can think this is the limit as n is growing. So depending on where you start, 2 to the n might be n factorial, I think. But if it's a race to infinity, then that factorial is going to win. So in this case, the denominator is bigger, which means it's convergent. Okay, that's the harmonic series. There's also this idea of a telescoping series, which 1 over n to the n plus 1. You could use partial decomposition of fractions. And let's say an plus a plus bn equals 1. So a is equal to negative b, a is equal to 1, b is equal to negative 1. If that's confusing, you can go back and watch something on partial decomposition of fractions. But that would mean that another way of writing this would be 1 over n minus 1 over n plus 1. The sum as n goes from 1 to infinity. And so if you think of what happens, I'm going to plug 1 in here. I'm going to get 1 over 1 minus 1 over 2. Okay. Then I'm going to end, my counter is going to go up. I'm going to get 1 over 2 minus 1 over 3. Okay. Then I'm going to get 1 over 3 minus 1 over 4. And it's going to keep going up like that. And if you get rid of the parentheses, then what you're going to notice is that these terms like these, they cancel out. Okay. And you can close your eyes and picture what's going to happen. Every single term after this first one is going to get neutralized. And so sometimes you can use a telescoping series to show convergence. And I guess that's like one of the trickier ends. That's like on the trickier end of the spectrum. And I would liken it to, there's a way you can find an integral. Like one of the last things we showed in chapter 7 was partial decomposition of fractions. It can work in these infinite series because these infinite series are a lot like integrals. And the next thing that I want to show is the last thing is just that it's the integral test. And if you think of, if I had this f of x is equal to 1 over x squared, and I was trying to, let's say, approximate the value from 1, this is 1, all the way to infinity. Well, how might I do it? Well, I might do like a Riemann sum calculator, right? And what would this be? This would be 1 over 1 squared. This would be 1 over 2 squared. This would be 1 over 3 squared. This would be 1 over 4 squared, okay? So what you can see is that the approximation of the area of this integral from 1 to infinity of 1 over x squared dx is approximated by, where is it? By this series right here. And so the integral test, which I'll tell you is kind of like a conduit, the integral test, it's important to understand conceptually why it works. But when we get to the tests that are going to come after this, those are the ones that you're usually going to use and you're going to cite when you show a test converges or diverges. But the integral test says that if you have a series S with a to k with decreasing terms, where f of n is equal to a and f is a continuous positive decreasing function over the interval from k to infinity, if the integral converges, then the series also converges. And it says if the integral diverges, then the series also diverges. And so this was, I dropped a hint before, like I could say, sorry, not the, if I had the sum of 1 over n squared, n equals 1 to infinity, this you could say converges because of int test. I'm not going to do the integral test, but you could. And if I had the sum of 1 over n, this goes from n is equal to 1 to infinity. This could say diverges because of integral test. And by the way, what you would want to show in the integral test is in this one, you would want to do the integral from 1 to infinity of 1 over x squared dx. And in this one, you would want to do the integral from 1 to infinity of 1 over x dx. And I think we had a part in the book so far this year, which we may have skipped over, which is like, or I don't know, we may have, we may not have, but if I had the integral from 1 to infinity of 1 over x to the p, where p is not a variable, p is just some constant, dx, when does it diverge and when does it converge? It will converge if p is greater than 1, diverge if p is less than or equal to 1. And really, we're not, I mean, if I make p available in the negative spectrum, it just makes it confusing. But like, you could write a different one where it's x to the p if p is, no, my eraser's not working. Basically, I want to switch the sign. P is less than -1 or p is greater than or equal to -1. But then we're only talking about the negative spectrum. So the P series test is that, which I just kind of like, it's just shorthand for what you already know about the integral tests and the convergence and divergence of those types. I think that's where I'm going to end it now. And I guess we'll when we go on, we've got limit test, we've got limit comparison test. Well, we got the comparison test. Let's see. We've got the P-series test. We have the limit comparison test. We have the ratio test. And you don't need to know all those yet, but it's good to know that they're coming, I think.